Hello, everyone. Good morning, good afternoon, and good evening, and welcome to our today's webinar. My name is Carmen Guguta, and I'm a Technobis Crystallization Systems Head of Business Development and Marketing. And together with our presenter today, Professor Joop Horst from University of Rouen, we are bringing to you the webinar on a structured approach to cope with impurities during industrial crystallization development. Just before we start, I would like to share with you a bit of information about the webinar. The webinar is being recorded and will be made available to all of you. Tomorrow you will receive an email with a link to the recording and also to the slides kindly provided by Professor Joop Horst. Also on our website, starting tomorrow, you will be able to view the recording anytime you would like, the same way as you are used with all our webinars. If you have a question during this webinar, please make use of the chat function of this webinar platform. After the webinar, please feel free to write to us anytime at info@crystallizationsystems.com or directly to Professor Joop Horst. I think he will also share his email address shortly on his slides. So you will be able to contact him directly as well. The webinar will last about 45 minutes. And just before we start, I would like to introduce to all of you Technobis Crystallization Systems briefly. And Technobis Crystallization Systems is a Dutch company located in the north of the Netherlands. And I wanted to share with you this picture today, although it's not the best picture ever and the weather didn't help today. But this is actually what we see from our offices, the flower fields. This is the time of the year in the Netherlands when you see in many parts the flower fields. And I hope I was able to cheer you up a bit, despite the challenges that this pandemic is bringing to us since more than a year ago. Well, Technobis Crystallization Systems is a world-leading technology provider for solid-state research, process development, and formulation. I'm proud to say that since 2005, we have installed more than 500 instruments in nearly every pharma lab around the world. Our product portfolio comprises 3 products at this moment: Crystal Breeder, Crystal 16, and the Crystalline instruments. Most of you already have a Crystal 16 or a Crystalline, or maybe even both of these instruments in your labs. Maybe there are a few of you that you do not have an instrument, and if after this webinar you think you would like to test one of our instruments, please contact us either directly via the website, it's very simple, or with an email at info@crystallizationssystems.com. In the meantime, please remember, the Crystal 16 is your instrument for solubility, metastable zone with determination, any type of solid state type of screening that you would like to perform. This is your instrument, the Crystal 16. And the Crystalline with the camera technology, with the particle view imaging that works exactly like a microscope, and with the Raman, the possibility to connect it to a Raman spectrometer, will help you to develop or optimize your crystallization or formulation process. Technobis, as you know, is a manufacturer of lab instruments which enables you to measure, characterize, control some of the parameters, properties, if I can call them like this, related to crystallization. And I'm sure you'll hear much more about it during the webinar today. Now, this was about Technobis. Now it's time to introduce our speaker today, Professor Joop Horst. Professor Joop Horst started a new position actually this year at the University of Rouen within the Laboratory of Separation Science and Methods, continuing his work on industrial crystallization fundamentals. His research group identifies and applies fundamental knowledge relating particulate product properties, crystal structure, and product molecule for the optimization of innovative crystallization processes. Most of you most probably know Joop Since his time at CMAC, his research group was part of the Center of Continuous Manufacturing and Crystallization, CMAC, a large Strathclyde-based center on advanced pharmaceutical manufacturing. He was also coordinator of Horizon 2020 Innovative Training Network core on continuous resolution and de-racemization of chiral compounds by crystallization. A network consisting of 15 PhD students, 8 academics, and 7 industrial partners. And I think this is just the 1% I could say in a few minutes about Joop and his achievements. Is much more to say. And we are proud to be able to have him today as a presenter and to present a topic to bring it to you today. Joop, thank you very much once again for doing this for us. Thank you for helping us and being out there and supporting us, and for being in this webinar today. I am making now you a presenter, and I'm giving the floor to you. And I think now you should be able to share your slides. Just you are also muted, so please unmute yourself. Yes, now we hear.
Thank you, Carmen. This nice introduction. So I'm planning to talk about the structured impurity rejection approach in industrial crystallization development. And yes, I changed location. Maybe not yet in reality, only virtually, but I started a new position at the University of Rouen. So I'm actually in the process of changing from haggis and whiskey to Camembert and Calvados. So going from CMAC to the University of Rouen, the laboratory. I discuss mainly 2 articles today. The main part is an article on in OPR&D, and it's a structured approach to cope with impurities during industrial crystallization development. It's mainly the work of the postdoc Stephanie Irwin, and she moved on to a postdoc position at the University of Oxford last year. This research was done within CMAC, and we had great help of the industrial partners of CMAC, so Bayer, Pfizer, and Lilly mainly. And then we had some sponsoring from the EPSRC. And the other article is an article in Crystal Growth and Design from my PhD student, W.W. Lee. He finished already some time ago, and we managed to publish this article just in January this year on a screening approach for identifying co-crystal types and resolution opportunities in complex chiral multi-component systems. This research was performed at the University of Technology with participation of the University of Nijmegen, and it was sponsored by the Dutch Science Foundation. So I divided my talk in 4 parts, and the first part will go deeper into the industrial crystallization and its relation to impurity rejection. So industrial crystallization is a process where you make crystals, and these crystals are formed because you have nucleation, crystal growth, agglomeration, and secondary nucleation taking place in the crystallizer. And all these sub-processes of crystallization are governed, are controlled by the supersaturation in the solution and the fluid dynamics that take place in the solution. And then you get a solid from this crystallization process, and this solid will have a certain product quality. And next to this solid that has a certain product quality, a particular product, we want to produce a certain amount of this, so the productivity, say a certain amount per liter per hour. And then we want to crystallize as much as possible. So we want to have high yields, so that we crystallize as a large amount of the solute into crystals, so that not a lot remains in the remaining solution. So product quality can be divided into 4 key product quality aspects. So next to form, solid form, crystal size distribution, and crystal product shape, there is a product purity. And we would sometimes forget almost that crystallization is actually a separation technique that reaches a very high solid purity in just a single process step. So these 4 key product qualities are related to secondary quality aspects such as dissolution behavior and filterability. So we could define for a certain crystallization process some specifications to use in a basic process design. So we can say, for instance, that we want a productivity of more than 12 grams per liter per hour and a yield of 80%. So we crystallize 80% of the solute. And we should have a crystal product that should contain less than, say, 0.1 weight percent of a specific impurity. So those might be specifications you start with when you want to do a basic process design. So what you're actually doing in a crystallization process is that you split up the feed solution into 2 parts. You split it up into a particulate solid and a solution. And then the remaining solution contains the same components as the feed. So we have the solvent, we have the impurity, and perhaps some solute is also left in the remaining solution. And then the final product contains mainly the crystallized solute, but might also contain some impurity. So now we can quantify this impurity rejection. So most of the impurity is left in the remaining solution, but we want to quantify how much ends up in the product in respect to the remaining solution. So we can describe that with distribution coefficients. So we have a distribution coefficient for the impurity. So that is how much of the impurity ends up in the product in respect to how much it ends up in the remaining solution. And we want that distribution coefficient to be as small as possible. We don't want impurity in our product. And then we have the solute, and we want to crystallize out as much as possible there. So we want to have a large distribution coefficient of the solute. So we want to have as high concentration of the API in the solid compared to that in the remaining solution. So we want to have a large distribution coefficient of the API. And then we can define a selectivity. So that selectivity is the distribution coefficient of the impurity in respect to the distribution coefficient of the API. So we want to have a very low selectivity. So we want to for the solid to be very selective towards the solute and not towards the impurity. So we want to have a very small value for our selectivity coefficient. So let's then assume that we have a yield of 80%. And that allows us to do some calculations. So we can use a simple mass balance and then determine the selectivity coefficient you need when you start with a certain impurity feed and you want to end up with a certain purity in your crystals. So that is shown in this graph. The lines represent particular product purity, and then you see the selectivity coefficient shown as a function of the feed concentration, the impurity concentration in the feed. So to give an example, at an impurity concentration in the feed of 0.1, you would need a selectivity of about, say, less than 0.12 for a product purity in your crystals to be more than 95%. So that is the point, the yellow point. If you want higher product purities, you have to somehow increase your selectivity coefficient. So in this analysis, we assumed that the solvent did not end up in our crystals to make it relatively easy. But the solvents could also be, say, an impurity, of course, and then you can consider it within the balance. The selectivity coefficient is a good measure for impurity rejection, and it accounts for the product and the remaining solution concentrations. So you have this balance, say this distribution over the two phases, which you then capture well with the selectivity coefficient. And we can determine a target selectivity coefficient from the process design specifications through a mass balance. And then we can also determine the real selectivity coefficient experimentally. And of course, depending on the crystallization conditions, these selectivity coefficients can vary. So in this particular case, we crystallized phenofibrate in the presence of its acid impurity. And with a particular cooling crystallization step, we crystallized a certain amount of the phenofibrate and then determined the concentrations in the remaining solution and in the solid. And we have the amount of solid that is formed. So we can determine the distribution coefficients. And from the distribution coefficient of the phenofibrate and the impurity, we can determine the selectivity. And that selectivity is 0.044. It's a relatively small selectivity. So that is all. That's what you can do with the mass balance, and it helps already quite a lot. But we have to find ways to get rid of impurities and improve impurity rejection. And we can do that by following a workflow procedure. And this workflow procedure we defined actually looks at the mechanism of impurity incorporation. And impurity can end up in a crystalline product in many ways. So the impurity could just be adsorbed on the surface of the crystals, and they might be easily removed through proper washing procedures. And the products might also agglomerate, which makes that solution and impurity end up at the points where the crystals are cemented together. then preventing agglomeration would improve purity. And then we have inclusions that could compromise the product purity. And these inclusions might form due to attrition of crystals to the stirrer, or due to harsh crystallization conditions, high supersaturations, large growth rates, or really due to the presence of an impurity that generates macrosteps, and these macrosteps then generate inclusions at the interior of the crystal. So for these inclusion formation mechanisms, finding better crystallization conditions can improve the purity. And then you could have impurity crystals concomitantly crystallizing with the main product. So the impurity then forms crystals itself. You could also have the impurity form a co-crystal with the main compound. And I hope to come back to that in the last part of the presentation. And then finally, the impurity might incorporate into the crystal lattice. So all these different mechanisms are connected to a different way of alleviating the impurity from the crystal product. So you have to identify the incorporation mechanism before you can use a procedure to alleviate the impurity. So our workflow is directed towards identifying this impurity incorporation mechanism. And then we can get to the goal, which is the crystallization that gives a good impurity rejection. So the impurity rejection workflow is shown here on the right. It may be a bit small, but I'll guide you through it in the coming slides. So the goal is that crystallization gives a good impurity rejection. And then we have different stages. And these stages give approaches to gather specific information on the limiting impurity rejection mechanisms of the system. And then we have decisions that we make based on the information from the stages, so that we can go into the right direction in the workflow. So stage 1 of the workflow is prior knowledge. So the objective is that you collect physical data and you develop analytical methods that are required to carry out the workflow. So you, for instance, would need solubility measurements and say crystallization product specifications, such as the preferred purity of your final crystalline product, in order to be able to go through this workflow. Point 1 is very important, of course, and point 5, analytical methods for identifying the amounts of API and impurities is also important. So you can use, for instance, HPLC for that. Then the second stage is to do crystallizations in order to see whether impurity rejection is a problem. So we want to determine the selectivity, and that can be done by performing a crystallization and looking at the impurity concentration in the solid and in the remaining solution, and also the solute concentration in product and remaining solution. And that leads to distribution coefficients and to a selectivity coefficient. And then we can make a decision. So does this selectivity we determined experimentally suggest a good impurity rejection, or or does the impurity rejection have to be improved? So do we have a selectivity which is much smaller than our target selectivity or not? So if the selectivity is much smaller than our target selectivity, then everything is fine and we are already finished with the workflow. But if it is not, then impurity rejection is a problem. We don't reject enough impurity. So we have to go through further through the workflow to stage 3. And stage 3 is a simple assessment of the occurrence of agglomeration. Does agglomeration occur or not? And if agglomeration occurs, you can count on it that impurities are present in the solid due to this agglomeration process. So so resolving the agglomeration resolving the agglomeration to obtain non-agglomerated products helps to alleviate the impurity incorporation and get to a better impurity rejection. So we have the decision number 2 here, that if you do see agglomerates, then you follow an anti-agglomeration strategy to get rid of the agglomerates, and in this way improve impurity rejection. And if you don't see agglomerates, then the impurity presence is due to something else, and we have to go to stage 4. And in stage 4, we investigate surface washing. And for surface washing, with the surface washing, you remove any impurities deposited or adsorbed onto the surface. So what you do is actually suspend contaminated crystals in a saturated API solution, and that should remove impurities from the crystal surface, at least partially. So if you see a large increase in the concentration of the impurity in the solution, that is a strong indication that surface adsorption is the reason for the impurities, the impurity presence in your product. So does the impurity concentration in the solid reduce by 50%? That is the question. And if that is so, then we can be sure that surface adsorption is the problem, and a proper washing procedure can get rid of many of the impurities. If this is not the case, so if it is not surface adsorption, we can have a look at how these crystals dissolve, and then we can map the impurities there. So we examine in this stage the distribution of impurity throughout the crystal bulk. So what we do is to suspend crystals in a saturated solution and then increase the temperature, so increase the solubility, so you partially dissolve these crystals. So you can actually slowly dissolve these crystals if you slowly increase the temperature. And during this process, you can measure the concentration of the impurity, and how the concentration of this impurity increases with the amount of crystals that is dissolved tells you something about the incorporation mechanism of these impurities. So if all the impurity directly is dissolved, then we have surface adsorption, which we should already have encountered in stage 4. But if it takes a bit longer, say from 20 to 40% of crystals dissolved in order to reach 100% impurity dissolved, it might be inclusions that are formed due to attrition that caused the impurity in the crystal. And then if it reaches later 100%, it might be inclusions due to impurity or harsh growth conditions that cause the impurity on the inside. And then if you have a more even distribution of the impurity in the crystal, so that you have a relatively straight line going from 0% crystals dissolved to 100% crystals dissolved, you might have a solid solution. So then we come to decision 4. Is the impurity present throughout the crystal bulk? And if that answer is no, we would have either surface adsorption, inclusions due to attrition, or inclusions due to impurities and harsh growth conditions. And otherwise, we would have a solid solution. So if we have a solid solution, we have another decision to make. So if then we have material present with different impurity levels, we can go to the next stage. If not, then yeah, it's a bit difficult to continue this workflow. So then we can go to stage 6 if we have different levels of impurity in our solids. So then we can look at the solid state interactions and the mechanism, the formation of solid solutions. So we actually are looking to determine the binary phase diagram, and this binary phase diagram then gives information on how one component, the impurity, distributes into the solid of the other. So we can have a very simple eutectic system, which is the left diagram. So then you would hardly have any impurity in your solids of the API. And then in the middle, you have a partial solid solution. And in that case, it's very difficult to get rid of the last, say, remaining concentrate levels of impurity. The impurity thermodynamically incorporates into the solids, and that is relatively difficult to get rid of. And then you can, of course, have complete solid solutions, and it's even more difficult to get good levels of impurity rejection. So then we come to decision 6. If we have any evidence of a solid solution, if there's no evidence of solid solution, we can change the process conditions and hope to get better impurity rejection from that. And if it is a solid solution, we would have to change the feed of the crystallization process in order to be able to reach proper impurity rejection. Say a solid solution indicates that perhaps you have to remove the impurity from the feed before you do the crystallization process. Good, so these were the steps from the workflow. It's a general workflow that can rapidly identify the mechanism of impurity incorporation responsible for poor impurity rejection. And there are only a few general experiments needed with standard laboratory instrumentation to come up with good conclusions on the impurity incorporation mechanism. So it gives you a structured approach to deal with impurities. So then I come now to an example. So this example looks at paracetamol and impurities. So let's look at stage 2. We have some information gathered in stage 1. And in stage 2, we want to crystallize in a very controlled way. So one thing we can then do is look at the solubility of paracetamol, in this case, in 2-propanol, and look at the induction time probability, so that we find conditions where we nucleate within, say, 30 minutes every time that we crystallize. So then we can come to a certain cooling profile that we can use to do some crystallization experiments. So this cooling profile consists of a dissolution stage and then a nucleation stage at constant temperature to make the nucleation as consistent as possible, and then a growth stage of these crystals. And then we can use an isolation procedure from the literature. And we can crystallize in the presence of impurities, for instance, the impurity acetanilide. So it resembles paracetamol quite a lot, and if we do the crystallizations, most crystallization experiments end up with a relatively low selectivity. So we have substantial impurity rejection, but we could look at whether it can be improved even more. So in stage 3, then we look at agglomeration. So we can visualize under the microscope the product, and we don't see a lot of agglomerates, so no agglomeration found. And then we looked at stage 4, surface washing. And in the surface washing, we see that we can considerably reduce the amount of impurity that is adsorbed on the surface. So a way to get rid of acetanilide is to modify the isolation procedure for better impurity rejection. Then we have another impurity in paracetamol, so metacetamol. It's also an impurity that resembles paracetamol quite a lot. So this has a little bit larger selectivity as determined selectivity measurements. So we have relatively poor impurity rejection. So can it be improved? Then we look at agglomeration. So we don't see agglomeration in the pictures. And if we do surface washing experiments, so we suspend the crystals in a saturated solution, and then look at the concentration of impurity in the solution, then we see that that the impurity remains to a large extent in the crystals. So we do have some surface absorption, but mostly impurity is present at the interior of the crystals. So then we can continue to stage 5, where we look at the impurity mapping. So we would gently dissolve the crystals in an initially saturated solution by increasing the temperature. And then the concentration profile of the impurity tells you how the impurity is distributed within the crystals. So that indicates that that we do have surface adsorption, as we saw previously, but also that the impurity is distributed quite evenly over the crystals, as it increases from 0.5 to a little bit above 1% quite gradually. So we could say that from stage 5, we could say that we have some surface adsorption, but the impurity seems to distribute throughout the crystal interior, and that indicates that solid solution is occurring. In order to look at solid solutions, we can look at the solid state behavior. We can determine a Taman plot, so that's the plot on the lower right, by doing differential scanning calorimetry. So here you see a DSC from a mixture of impurity and API, and you see say 2 events, and one is indicating the eutectic temperature, and the other is indicating the melting temperature. And now we are looking at the peak area of the eutectic peak, and that we would plot against the impurity concentration. And you then get a whole bunch of points through which you can draw a line from, say, the eutectic composition at 0.6 to 0. And we see that there is a small region where between the intercept of this line and the axis of 0. This strongly indicates that there is a solid solution for this system. So then we can conclude from stage 6 that we have a partial solid solution has formed between paracetamol and metacetamol. So this means that it is very difficult to get rid of the last traces of metacetamol, say about the last 5% or so. And then it is good to think about other ways of removing the impurity from the feed solution to the crystallizer before you start the crystallization process. Good, that was an example of the application of the workflow. And then I come to my last part. It's about a racemic compound in chiral separation. So a chiral compound molecule comes in 2 forms, a left-handed and a right-handed form, and similar to hands, these enantiomers are each other's mirror image, and they cannot be superimposed over each other. So many pharmaceutical molecules are chiral. While one enantiomer might fit in a biological receptor, the other might fit not, and due to its different 3D configuration, this means that the pharmaceutical activity can vary depending on the enantiomer. While one enantiomer has the preferred pharmaceutical action, the other might well have less beneficial interactions. So a striking example was thalidomide in the 1960s, where one enantiomer was effective against morning sickness for pregnant women, but the other caused birth defects. Another example is, for instance, ethambutol, where the S enantiomer is used for tuberculosis treatment, while the R form might cause blindness. Regular bodies and pharmaceutical industry realized that enantiomer products are preferred over racemic products. So over the years, many racemic products switched to enantiomer products. And you see now that new chiral pharmaceuticals are predominantly marketed as enantiomer products. So we need to be able to produce enantiomer pharmaceutical products. And crystallization is the optimal process to do just that. So here you see a crystal lattice of only left-handed molecules, and you will see that a right-handed molecule has difficulty fitting into this lattice. So the chiral selectivity of enantiomer crystals is very high. So we can base chiral resolution or chiral separation on this selectivity. So we start with a racemic solution of both enantiomers. So we have 50, let's say 50-50 mixture in a solvent. And then we would crystallize left-handed and right-handed crystals, forming a conglomerate. And if we prevent the formation of the red crystals, we only crystallize the blue crystals. And we end up with an enantiomer product. Unfortunately, only 10% of the chiral compounds form such conglomerate systems. 90% of these compounds form racemic compounds. And racemic compounds contain both enantiomers, so there's no separation power for these crystals. Actually, this is coinciding with what I saw, what I showed as a mechanism at the start, where we form a co-crystal. So actually here we form a co-crystal of the two enantiomers, and that is very difficult to get rid of this impurity enantiomer. So one way of getting rid of this enantiomer is to make a co-crystal salt or solvent from it. And if you're lucky enough, then you form a conglomerate co-crystal, solvate or salt. And then you again have left-handed and right-handed crystals. And if you prevent the formation of one of them, you can form you can crystallize an enantiomer product. So the pharmaceutical Ibuprofen is a racemic compound. It is also marketed as a racemic compound. So you have two enantiomers in the crystal product. So what we did, we looked at the formation of a conglomerate system for this compound, racemic compound Ibuprofen. So we added a coformer that is BPE, as we call it, to the two solutions of Ibuprofen in order to be able to form to look at whether a conglomerate forms. But this is a rather difficult system because you have a solvent, the two enantiomers, and then the coformer, BPE. And then we do clear point measurements, so we also vary temperature. So we have a quaternary phase diagram with the additional variable of temperature. But still, if you do it schematically, you can do very nice measurements in here. So let's look at, we crystallize from heptane, and we can start with a racemic solution and determine the clear point of a composition with a certain concentration. So we chose the composition of 114 millimoles per mole of Ibuprofen, and if we measure the clear point, so the point where a suspension turns into a clear solution upon increasing the temperature, is 40 degrees. So we can also look at compositions with the same amount of chiral compounds, but then a different ratio of the two enantiomers. And we can plot that, say, we can plot then the clear point as a function of the ratio of enantiomers. So at 0, we have only R enantiomer in the solution. At 1, we have only S enantiomer in the solution, and at 0.5, we have a racemic solution. So the blue point is at 40 degrees because that we measured already. So then we increase the amount of S and decrease the amount of R, and you see a decrease in the clear point up to a eutectic point, after which you see an increase again. So this behavior is really characteristic for a racemic compound. So ibuprofen is a racemic compound. So now we can add the coformer in the background, a little bit of coformer in the background, and we chose to add 28 millimoles per mole of BPE. And if we measure then the clear points, we see the red points appearing. So these red points show a V-type profile, and that is very characteristic for a conglomerate system. So actually, by adding this compound BPE in the background of the solutions, we form a conglomerate co-crystal system. So we have a conglomerate ibuprofen BPE co-crystal, and that can serve as the basis for a chiral separation process design. We have actually this solubility data, so we can use it for the chiral separation process design, and also to further explore the solids. You can determine, you can prepare single crystals. Say a workflow how to discover such new solids is described in this article of Wei Li and Mariette de Groen. So that brings me to the end of my presentation. So I had 4 topics on impurity rejection, and if you want to be challenged even more, then you can look up this article on phenanthrene and amaze yourself on how large effects on the phase diagram these small amounts of impurities can have. So I thank my co-authors and the funding and all the people involved, and I also thank you for your attention.
Thank you very much, Joop. A really nice presentation. We have quite a few questions, so I will already start with some of the questions. I'm not very sure if we can cover all of them. We'll try to read them to you. One of the first questions is, what is the smallest crystallization scale you would recommend to start investigating the impurity inclusion mechanism?
You would have to adapt this to your say detection limit of the analysis tool. So we performed crystallization experiments in the crystal 16 and the crystalline. So say 0.5 milliliter to about 8 milliliter. That is a nice convenient amount to use.
Okay. Another interesting question from Sean Kinnan. How would the crystallization workflow proceed if your product was a low melting wax?
Low melting wax, yeah. So that is a challenging compound.
Yes,
So
indeed.
you could be quite sure that you will have a lot of impurities incorporating into such low melting waxes, and here you have very high solubilities and difficulty in crystallizing, and perhaps a lot of high risk of solid solution formation. Yeah.
Yeah, indeed. I also have seen during my previous jobs quite a number of materials that we received as wax, and it was really a matter of purification to get it into a nice crystallized powder, but it is not a straight forward thing. It's quite a challenge, and it highly depends on the compound, on the API, or what is the main compound that you're working on.
Yeah, you might want to switch to crystallization rather than solution crystallization for low melting waxes, of course.
Yes.
And then you might get a better impurity reaction.
Yeah. Another question. How are the selectivity lines obtained experimentally? I think you had on one of your slides.
So the lines, they were determined with a mass balance. And the points you can determine with experiments. So it is just that helps you.
Yes.
The mass balance gives you these lines, and then you measure the selectivity, and that gives you then a point. So then you can see how far away you are from your target selectivity. If it is very difficult to reach impurity rejection, or it is relatively close by to the target.
Another question, because you are on this slide, I see another question related to the XIF here. How do you put together the XIF versus selectivity coefficient graph?
Yeah, it's a mass balance. So the mass balance is on the left in the slide. You have the compositions in all three phases, and you have the amount of the three components in these phases, and they constitute the mass balance. You have to the mass balance is since we're not doing nuclear fission, the mass balance is there. So the amount you put in is the same as the amount you put out, get out. So that is giving you say mathematical framework to look at say a certain if you set a certain yield and you want to reach a certain impurity level in your product. So how much should the selectivity then be in order to reach that? And then you compare that to measurements, and then you can see whether these two are smaller or larger than each other. If your target selectivity is much smaller than your actual selectivity, you have to do some impurity rejection improvements. If your target selectivity is much larger than your actual selectivity, then impurity rejection is not a problem.
Okay. To apply DSC for understanding the eutectic point, what could be the threshold content of an impurity? Is it applicable if the impurity is less than 0.5%?
Yeah, DSC is maybe not very accurate if your impurity levels are very small. So then you have to go to another technique to find out whether you have a solid solution or not.
Another question related to the conglomerate co-crystal solvates. How can you ensure the solvate is of conglomerate and not a racemate?
Yeah, it is described in the article how you can get indications, and then to be sure is to make a single crystal and determine the structure. So if you find in the structure only one of the enantiomers, then you can be sure that your system is a conglomerate system.
How do you choose the amount of BPE to form a conglomerate co-crystal system?
You would use the solubility of the two components as a guide for that. So you check the solubility of, in this case, it was Ibuprofen in the solvent.
Yeah.
And then you solubility of BPE in the solvent, and you then take a certain reference temperature, say 25 degrees or so, and you make a solution with the saturation concentration at 25 degrees for both components. And that is the composition where you're most likely to form co-crystals. And so if you then measure the clear point of that solution, you expect a clear point that is much higher than 25 degrees, because if you form a co-crystal, you form a more stable solid. So you have to go to higher temperatures to dissolve that. So that would be my approach for determining whether you have a co-crystal or not.
Yeah, I think you also have a publication back in 2009, I think, quite some time ago, explaining this method. I can share it also with later on with the attendees.
It's titled Discovering New Co-crystals. Yeah.
Yes, indeed. Yes. I think it's also a webinar that you have, one of our first webinars done together with my colleague Danny. So if you are interested, the attendees are interested, they can have here the recording is available on our webinar, on our website, sorry, under the training and events. You have all the webinars there. One of the first ones at the bottom. In the same lines with these, how do you decide which co-former to use for chiral separation?
Well, that's a complex question. Well, you have to base your decision on experiments. The co-former has to, for instance, form a conglomerate system, and then this conglomerate system has to be possible to be used in preferential crystallization, for instance. So you would need then a large metastable zone with for these compounds in racemic solutions, so that you can seed supersaturated solutions with the preferred enantiomer, so that you can grow out these crystals without nucleating the crystals of the counter enantiomer. So yeah, it's a complex question worth another webinar.
in another project, right? It's another question. The questions are keep on coming, and I'm trying to pick up as many as possible. Is there a thermodynamic preference over racemate solvate or conglomerate solvate? Can it be predicted?
It cannot be predicted for the moment. No. So whether you form a conglomerate or a racemic compound is not yet really predictable. It is, yeah, so you have to do experiments in order to determine whether a certain compound forms a racemic compound or a conglomerate. And then changing such a compound in a conglomerate co-crystal, say a racemic compound in a conglomerate co-crystal, is also very difficult. It seems that you have less than say this 10% chance to form a conglomerate co-crystal rather than a racemic compound co-crystal. So it appears that say families of racemic compounds don't want conglomerate members, which is which creates a difficulty for chiral separation.
Another question, for slow dissolution experiments to determine the impurity distribution through the crystals, the assumption is all crystals, fines and coarse, dissolve at the same rate. Is this true? How far is this realistically observed experimentally?
Well, yeah, it's not. A lot of things can happen during this dissolution experiments, and these crystals can break due to the stirring, and smaller crystals can dissolve faster than the larger crystals. So it is it is not a very accurate experiment, but it gives you say an indication. And with this indication, you might want to explore further with more accurate experiments, or you might want to, maybe the indications for this from this experiment are enough to decide on which mechanism is which impurity incorporation mechanism is occurring. So it's good to realize indeed that there are some assumptions underlying this dissolution experiment, and it's good, to account for them.
I think we will stop here. We have a few more questions that I will share them with you after this webinar, Joop. We have a lot of people writing to us. Thank you for this excellent presentation. Another thank you. We are looking forward to see the recording and the slides to receive. So, and also from my side, thank you once again. Thank you very much. I think I cannot thank you enough, Joop, for bringing this webinar, and not only this webinar, to our customers and to our attendees today. What I would like to share with the attendees is that shortly next week we will start to promote our next webinar. Our next webinar will take place on the 20th of May on a Thursday. It is a webinar brought together with Johnson Matthey on multi-component pharmaceutical crystals, from solid form selection to controlled crystallization. If you are interested, check our website or stay tuned on LinkedIn. You will definitely hear about this next topic. Once again, thank you very much for this wonderful presentation, Joop, for this webinar, and stay safe and healthy, also the attendees, and hope to see you back soon at our next webinars.
Thank you.